All right, questions? You guys can prove rationality of, countability of rationals and countability of reals? Not yet.
If you do only countability of rationals, then
Yep. For the rationals, okay, so to show this, you just simply, you have to find the bijection from Z plus to Q, and then consider the table of A over B, A are ints, and B is not 0. So this is obviously not the table of rationals, but it includes, it's a superset of the rationals. And so we just go 0, plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 3 over 3. Okay. With the diagonals, D equal to A plus B, but where D equals 1 is only for 0. And so normally the way I do this is you could box them out, and so like here, that's the diagonal equal 1. This is the diagonal equal 2. Diagonal equal 3. Diagonal equal 4. Right? And therefore, all A over B are on some diagonal, right? There is no A over B that's missed, and that's the important part. And so this is your building process, is that you have to say we're going to find a bijection. The first thing we have to do is I'm making a table. 0 plus minus is the exact same thing as the book. We say what the diagonals are. They're A plus B, but D equals 1 is special. It's for the 0. Everybody else, diagonal 2 is only 1, 1, and then 1, 2, 2, 1, etc. And so we have all of these diagonals. The most important part about this is that, right? All A over B's are on a diagonal. And so then what we do is we go ahead and the whole point, countability means bijection. So we're going to make the bijection. And so from this point on, the bijection from Z plus to Q is to move along diagonals, etc. We've already done that, right? The rest of this is obviously you finish out. You just move along the diagonals. It's pretty easy if I'm just talking about it. I just simply say, I just count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, skip. But you have to talk about the skipping. Or if you don't skip, you have to say that I'm actually counting a larger set than the rationals, and since it's countable, the rationals are countable. So, but skipping is we're just making a bijection. Since I'm saying I'm making a bijection to Q, I gotta skip. If I didn't say that, then I could get away with, oh, this is bigger. But does that make sense in terms of the setup? Perfect. Okay. So there's a couple sentences that just need to be added to the finish part to explain how you count. And it's always fun. You don't have to do this, but always for myself, it's like one of the nice thing about countable sets is countable sets can always be put in roster form, right? You have first rational, second rational, third rational, etc., right? Which happens to be, what was it, 0, 1, -1, and then 1/2, -1/2, 2, -2, right? That's the nice thing about countability means there's an order. There's a natural order, and the order itself is designated by the function that you use to count.
I have a quick question. If you just had the fact that the set, that one set that's large and the rationals is countable, could you prove through like some steps with the sets that the subset of it should be countable too? Or do you have
That's
to?
a lemma.
Oh.
That's actually a lemma that you can show if you want. And the way that you show it is if you have a countable set, a subset, a proper subset must be countable by just simply count the bigger set and skip anything that's not in your smaller set. I mean, that's just removal. And so therefore, it still has to have a function. So the bijection is just simply, if this is the bijection of a larger set, if you go through a larger set and remove some of the elements, I didn't do anything, right? They just collapse naturally and it's still countable. So that would be a lemma that you would show, but we just assume it's true. Because it's pretty straightforward to show that. All right, any other questions? It's a good study technique. That whole left as an exercise to the student. All right, so exam 2. Again, 10 problems, plus our 1 extra credit. So there's 11 problems, 10 points, that means 110 points available, but 90 points is considered, an A, so still the same idea. Again, the extra credit's either all right or all wrong. For 2.1, which is the idea, we had sets, we had the idea of the comparisons, which was subset, proper subset, equal, the cardinality of a set. The other thing that we talked about was the power set. The other thing that we talked about was set 1 cross set 2, right? Cross product. So from that was the introduction plus the visualization. Things like when we talk about sets, we talked about lists, also called roster, set builder, and Venns, right? So those are all the ways of visualizing it. What is a set? How could you represent it? I could write them down. I could give you set builder notation. I could write a Venn diagram and put a bunch of dots and circles. I can ask if they're the same, or they're subsets, or proper subsets, or equal, or what's their cardinality. Cardinality at this point was finite only. Infinite was just simply not finite. We didn't do anything with that. And the power set and the cross products, those are the things that were introduced at this particular point. For this section, we'll have 2 problems. The first one will be a combination of representation with questions about, say, subset and proper subset, questions. It'd be something like this. For example, if A was equal to, say, 1 to everything up to 20, and say B was equal to all 2Ks such that K is a integer and K happens to be greater than or equal to -2 and strictly less than 20. Could you give me, questions like this would be, so here'd be a question. What would A intersect B be in, say, could you give me a set builder form? Could you give me a list? Could you give me a Venn? Or maybe all three. Later on on these intersections, and say things like, questions like, is A a subset of B? Is B a subset of A? Yes or no? I mean, this is more pictorial, like give me values, visualize what these things are. So if I would do something like a Venn diagram version of that, let's say I would tell you that the universe of discourse is all ints from, say, -10 to 40. And I ask for a Venn diagram. So you would do things like, okay, here's my A, here's my B, here's my U. What are things that are in A? This is a little bit much. I went 1 to 20, right? So you'd have A, you'd have 1, 2. Okay, what are the things in B? If you look at that set builder notation, what are the things in B? The evens from -4 to 40, right? So which are the ones that would be shared? What would be the intersection? That'd be things like, what, 2, 4, 6, 8, 10, 12, up to 20. I did it too big, right? Things that would be outside of it would be what? -4, -2, 0, 22, 24, all the way up to 40, right? What would be the things in A that are not in that intersection that we haven't written down yet? 1, 3, 5, 7, right? 9, all the way up to 19. What would be the things in the universe that are not in those sets? Everything else, which should be what? -10, -9, down to -5, and then a -3, and then a -1. But then 0, 1, 2, 3, 4, everything up to 20 is there. But then 21 is out here, 23 is out here, 25 is out here, all the way up to 39. Now, those are messy with the ellipsis type of stuff, but I would make it smaller. But the thing is that could you figure out what's where? Could you give me a set builder notation for one of the regions? Could you give me a set builder notation for, give me a list of the stuff that's in A yet not B? Right? Could you give me a list of everything that's in the universe but outside of those two sets? Or I might ask for set builder notation. In other words, or I might ask for all three, right? Give me the list, think of a way to write it with a logical of some sort, maybe give me a nice picture with Venn diagrams. It's one of those ones where it's pretty straightforward. I just give you, hey, look, maybe it's names of people, maybe it's chairs, it doesn't have to be numbers. If I do that, then it pretty much throws out set builder notation, right? So, unless I have this student is in a class type of stuff. So, the idea is, can you go from things that are this to this? And if you gave you one, could you give me the others? The second problem is going to be either a power set or possibly, say, a cross product of some sort, right? Type problem. They had ones like, they had examples of, could you give me the power set of say, the singleton A? What would that look like? And they also had things like, and they could even ask things like, maybe give that, or, another example would be, is the empty set an element, of course that's not the element symbol, element of the power set of the empty set? Just kind of playing around. I mean, the book did this a lot. Like, can you take the power set? Can you check to see what's in it? Give me everything that's in it. Things like that. I probably won't do a power set, but it's a good one to do because it makes you think hard for practice. So, And maybe a cross product, right? You know, what's the cross product? You know, give me the cross product of these things. What's in it? All right. Over 2.2, we get into the actual set operations. The true set ops finally are things like you go intersection, union, a set's complement, a set's difference. We'll have two problems here. The first one's going to be verify some set identities using logic with set builder notation. Okay, what do I mean by that? Like the one we've already did before. What would be A union B's complement? What do I know what the answer is? This is De Morgan's. So it's A complement, flip, intersect, B complement, right? And so what logic do you think I'll do? These are all elements such that it is not the case that the element is in A union B, right? What does it mean to be in the union? That the element is in A, look at the symbol, or, stay same direction, the element is in B, right? Is everybody okay with that being the union? But I wrote it's not the case and for some reason wrote an E. What's not that? What would I use? It's not in A and not in B. What logical thing did I use? De Morgan's. So it's not the case that E is in A, and it is not the case that E is in B. What does it mean to be not in something? That means you're in it too. That means E is in A's complement and E is in B's complement. But that is just simply what? Right? You'll have to do this for a couple. I mean, it's just logic. I mean, we're using the logical rules from the other ones. So look at the set identities. I'll just pick a couple of those. And you're going to have to verify them using these. Set builder notation with logic. All right, that'd be the first problem. The second problem is a Venn diagram and membership table. That would be, for example, could you give me a Venn for what is A's complement intersecting B complement? Could you give me a Venn diagram of that using a membership table? Well, we would look at that and say, I'm in A, not in B, not in A, B, not in B, not in B. Looking at that, the first thing I have to worry about is A complement, which is no, in, right? But then what's A's complement intersecting B? What would be 1 and 0? Anybody? What's 1 and 0? What's true and false? False. Uses the same logic. False and false. True and true. False and true. And then what would be the A complement intersects B complement? The opposite of that. So that's my membership table, but my membership table tells me to take the Venn diagram, right? And it would say, okay, here's my Venn diagram, here's my universe of discourse, here is A, here is B. When I write this 1, 2, 3, 4, what does 1 represent? The row 1, right? It's in A and B. What's 2? Row 2, which is in A and not B. What's 3? Row 3. It's not in A, but it is in B. And what's row 4? Not in either, right? Those numbers have meanings. So we have to know how they go. We label it appropriately. Now, what does the membership table tell me to do? Shade what? What am I in? 1, 2, and 4. So I'm here, here, and everything on the outside. Everybody okay with that? It's color by number. Now you could have made a Venn diagram without this. You would have had to do what? A's complement is everything outside of A. I'm going to intersect that with B. Well, what is everything out? What is everything outside of A intersecting B? Region 3. That's in B and outside of A. And then not that. Everything else. Right? And so I want you to be able to say, okay, know what the regions are by the membership table, but also know what the regions are by a picture. The reasons why these are nice is because, well, it's not that big of a deal if we have 2 sets. If we have 3, 4, 5, 6 sets, membership tables are essentially the only way to go. And they're still colored. It's like it lets you know what is going on in the regions. People always ask, like, what's the point of this? It's like, well, what if you asked people 2 questions in a survey? What can they do? They can say yes to both, yes to one, and no to one, right? Or no to both. And so if I tell you I asked 15 people of one, and so many people said yes, and so many people said no, and so many people said yes and yes, what am I really telling you? The cardinality of the regions. And so then we start to ask, what are the possibilities that people can say? So this is a standard application that we use for cardinalities and tests for intersections and things like that for surveys. It's a classic example that's useful. But we need to be able to at least get to that point. All right, 2.3, functions. There's only one problem. And this will be simply make a function. What does that mean? How many ways could you possibly give me a function? What did I talk about for functions? You could give me, it's a relationship of some sort, right?
List the items and say, this goes to here, this goes to
Yeah,
here.
those pairs, we could have arrows, A to B, A to C, right? We could have an actual what? Algebraic rule, if you want to do that. I don't care how you make your function, right? If you put an ellipsis, I better be able to tell the pattern. Make your function however you choose to make your function. That is, and I'm going to have some questions. On to, 1-to-1, both, neither. Man, there's a lot of options. It is onto but not 1-to-1. It's 1-to-1 but not onto. It's 1-to-1 and onto. It's neither 1-to-1 nor onto, right? I might ask you any one of those combinations. But the other thing is, it must be a function, right? And functions have a domain and a codomain. I will give you the domain and I will give you the codomain. And that means when you make your rule, it must be a function. What does that tell you about the domain? What if I said that what if I said this? F is 1-to-1 and not onto, and F is going to go from the ints to the positive ints. And this is what you gave me. 1, 2, 3, 4, 5, ... 1, 2, 3, 4, 5, ... arrow, 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 dot, dot, dot.
No.
Is it onto? Nope. But is it one-to-one? Yes, but what's the problem? It's not a function. Why is this not a function? Where are those? I need the entire domain. If you don't give me the entire domain, this is not a function, right? Not a function if you don't have entire domain, right? So you have to pay attention. I mean, I might do things like map the reals to the ints. Well, an arrow diagram is going to be difficult, right? You'll have to go to algebra, but we already have things that do that. What three functions did I give in an example in this section that map the reals to the integers? Floor, ceiling, and round, right? So you always have ways around it, but be careful, right? You'll have, oh, like, yes, I know what you meant, but you didn't give me the domain. It's wrong, it's not a function. If I notice that you did this, 3 goes to 4 and 5, it's not a function. And some people, like, I've had that before where they've written down some algebraic rules and it's like, the 3 goes to 2 places, you know, just because of the way they wrote like a plus minus type of thing. It's like, well, no. So be careful, make sure it's a function before you have it. And I don't care how you represent it. Arrow diagrams, algebra, lists of ordered pairs, we're good. Yeah, right here. Okay, like what? Ordered pairs for? One-to-one and onto? Okay, so say example. F from, what do you want to do? Like the ints to the positive ints? That is one-to-one and onto. If I had an arrow diagram, I would do this. Say, I need a bigger space here. Next page. So my left-hand side would look like this. Say -3, -2, -1, 0, 1, 2, 3. Is that my entire domain? All right, my codomain, 1, 2, 3, 4, 5, 6, 7, 8. Right? And so what I'm going to do is I'll say, okay, I'm going to map 0 to 1, and then I'm going to map my positive numbers to the evens, and I'm going to map my negative numbers to the odds. Right? Does that, here's my question. Are you okay with me using 3 dots now? Do you see the pattern? That's the hard part, is do you see the pattern? Now, how many ways could I say it? I could say it, right? I'm going to say that 0 goes to 1, and then from this point on, I'm going to, so the second thing I'll do, this will be my rule, and then from here on out, I'm going to map the negatives to the odds, and I could give them ordered pairs. Say, for example, -1 goes to 3, -2 goes to 5, -2 goes to 5, -3 goes to 7, -4 would go to 9, right? And then the third thing I will do is I will map positive to evens. But what does that mean? That means I have 1 is going to 2, I would have 2 going to 4, I would have 3 going to 6, I would have 4 going to 8, dot, dot, dot. Hey, you guys saw the pattern, so obviously I can put my ellipses. So that would be an ordered pair version. This would be using words. You can explain to me in words what your function does. Right? Now here's a more fun one. Could you write a function that's an algebra that does that? Maybe go do that for fun at home.
You absolute value k plus 1 for the negative and the odd, and then
Okay. So you would say that's piecewise defined. You would say f of x, algebra. So f of z, right, is 1 if z equals 0. You said it was 2z if z is strictly greater than 0.
absolute value of plus 1.
Would that have worked for 0 too? Plug a 0 in there, that maps to 1. So we probably, yeah, we could have said this one and then just did that. But, yeah.
Zero would have worked on either.
Yeah, that's true. So 0 works in either of those rules. So negative 1 does go to 3.
Oh, wait, no, it wasn't.
Okay. Could you make this, say, not onto? Not onto means that I shouldn't use everybody on the right. What's the easiest thing to do? Take that thing on the right, shift it up 1. So that you don't, nobody goes to 1. 0 goes to 2, 1 would go to 3, right? You just simply move it up 1 or move it up a couple spots, and you don't go to those, it's not onto. How would you make it not 1 to 1? How about you map 1 to 2 and negative 1 to 2? And then 2 to 3 and negative 2 to 3? Right, that'd be not onto, that'd be not 1 to 1. Right, and so there's questions on these, it's like, and this would be algebra. It's not the only way to do it, but. Is everybody okay with that? I'm surprised at how often people go straight to the algebra and try to come up with a really complicated problem when it's just, sometimes it's like it's easier just to draw, like here. It was easier for me to think of drawing pictures, and then from my pictures, ordered pairs made sense, but once I did that, the algebra fell out. So, anyways. 2.4. Which is sequences and sums. What's everybody's favorite? We'll have 3 problems. Problem 1. I will give you a sequence rule, or rules, and you just give me the numbers. So example. 2n plus 3, where n is equal to 0, 1, and 2. What's my sequence? Right? Something that simple. I mean, might even be a couple that'll be that simple, right? Here's an arithmetic, here's a geometric, things like that. Can you follow the rules? If it's, I will probably do a closed and then an open. Say that, say, a sub 0 is equal to 1, a sub 1 is equal to 2, and then a sub n, a sub n is equal to twice a sub n minus 1, say, minus a sub n. Could you follow that rule? 1, comma, 2, comma. What's the rule? What's the rule? The rule says if I'm here, that's 1 before, that's minus. Is there a minus 2? I wrote minus 2, but I didn't get you over there. You need to stop writing on that. There we go. What are we supposed to do? Take 2 of the previous one and then subtract. So I would take 2 2's and then take away 1, which gives me what? 3. Then I would take which is, then I would take then I would get, hey, that's kind of fun. That's a really complicated rule for 1, 2, 3, 4, 5, 6, 7, 8, 9. Can anybody guess? Could you give me a close formula for this? What would be the 10th number? Okay, what would be the case number? Okay, so this would be okay, all right. Anybody? Uh-oh. That was n equals 0. That was n equal 1. That was n equal 2. It is k plus 1. For k starts at 0, 1, 2, etc. These would generate the same thing. This would be open. That's an open form. Closed of the same. Anyways. Second problem would be like what we just did. If I give you the sequence, can you give me the rule? Either open or closed. So if I gave you the sequence, here's the numbers from 1 to 10. Give me a rule that generates it. All right, that's recursive, which would be 1 plus the one before, right? So, anyways, so examples of like that. Could you give me a rule if I gave you, say, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. Obviously, you see that ellipsis. Everybody could write the next numbers. Here's the more interesting part. Could you think of some sort of rule, and these rules don't have to be algebraic like we've been doing. You could use a verbal rule. What am I doing to form that sequence? If after every one, I add a increasing number of zeros. First 1 0, then 2 zeros, then 3 zeros, then 4 zeros, then 5 zeros. I can't imagine, if you want, think of an algebraic rule. But you could say that, right? You also have, yep.
We can write it down just like you said it.
Just like I said it, right? Most likely I'll be more, I won't try to give you too much time because it does make people think hard. Well, how do I write that? We'll try to I'll stay in the ones that you've at least worked on. There was a homework problem like that, though. All right, the third one will be a sum. And it will be, you doing telescoping some? Let's do a telescoping. All right, 2.5, cardinality. This will be prove Q is countable, exclusive or R is uncountable. I'll do one of these, right? Well, no, you have to say exclusive or. It's pretty obvious. I'm only going to do one problem, so that's obviously, I'll just say the English word or. Or. I'll pick one of those for this problem. There's only one problem. That one. 2.6, matrices. That's again one problem. Basically, this is I'm going to give you A and B, and you're going to need to find A plus B, A times B, A, what's that called? Meet A, join A, Boolean product. So obviously my A's and B's are just going to be a bunch of zeros and ones. That way I don't have to have like a bunch. The first two, it's the number 0 and the number 1. For the last three, it's the bit 0 and the bit 1. That's called laziness on my part. To show me that you can do all the ops. Extra credit. Here comes the fun part. Let me see. I said Q or R. which is going to be prove R is uncountable or Q is countable. Notice how the order is switched? Okay, problem 9 on the test is going to be either Q or R. Whichever one I pick, the other one's the extra credit. So, hey, if you're going to have to study both, you might as well get 10 points by knowing them both, right? And if you can't do it, you always can stop by for extra credit and try to get those points back. And if you can do it, it's just free extra points. Like, yay. Except this one obviously is right or wrong. Which of the two do you find is easier? Let's have a vote. The countability of rationals is easier than the uncountability of reals. Raise your hand. 1. All right, uncountability of reals is easier than the countability of rationals. A handful more. 5.
They're about the same.
Yeah.
They're about the same difficulty. I don't know because I don't know how to do either. So are you okay with those? These 11 problems? All right. That's it. There's no questions.